The other thing is that, as you know, the institute has given additional slots, which so far we have not used. Okay, we may need to use one or two of those slots. I think as per the timetable, there is a slot available on Friday evening from 8 to 9:30 and another on Saturday afternoon from 2 to 3:30. So I'll discuss the matter with Professor P.K. Das and we'll let. Alright, so last time we were looking at equations in a cylindrical coordinate system, and since we are dealing with rotating machines, it is useful to consider the equations in a frame of reference which is rotating. So this figure shows a stationary frame in blue, OXY. The z-axis is perpendicular to the plane of your screen. And this red axis, OX prime, Y prime, which has the same origin O, is rotating about the z-axis with angular velocity omega. So if omega is positive, it will rotate in the counterclockwise direction, as shown by this black arrow here and this black arrow here. And the OZ prime axis coincides with the OZ axis. So if you have a point P, its radial coordinate R and R prime are the same systems. Similarly, Z and Z prime will be the same. But if you look at the angle theta is measured from the axis OX. It is the angle between this line segment OP and OX. Whereas theta prime, the angle measured in the rotating coordinate system, I'm using cylindrical coordinates, is the angle from OX prime to OP. So this theta prime is shown in red and theta is shown in blue. As you can see that from this figure, theta is larger than theta prime by this amount, omega t. So here I made an assumption that at t equal to 0, the red frame and the blue frame coincide. So at t equal to 0, OX prime is at OX and OY prime is at OY. So the coordinate transformation is R prime equal to R. Theta prime is less than theta by this amount, omega t, which is the angle through which this axis OX prime has moved from OX in time t. And since we use the chain rule, I'm introducing a symbol t prime to indicate the time. So you can either look at, and of course omega vector is omega times Ez. So if you look at the unit vectors, they are the same. And even the R prime and R, the position vectors in the two systems are the same. The reason being that the origin is common. In the case of the Galilean transformation, there were two origins, O and O prime. So R prime and R were different, but here R is the vector OP. R prime is also the vector OP. Hence, but if you look at the velocities, okay, then if I use V prime for the relative velocity, if I don't like to use primes, I'll substitute the symbol W for V prime. Okay. We see that the dimensions apparatus. Okay. And these are the material derivatives. Now, we can have two descriptions. Any variable can be expressed as a function of R, theta, Z, and t, or equivalently as R prime, theta prime, Z prime, t prime. The first function is f1, the second function is f2. Okay. Using the chain rule, you can show that del del R and del del R prime are the same. Del del theta and del del theta prime are the same, and del del Z and del del Z prime are the same. So the grad operators are identical. Divergence operators are also identical. The difference comes in the temporal derivative. So as in the case of the Galilean transformation, you see that del del t, the temporal derivative in the stationary frame, is del del t prime, which is the temporal derivative now in the rotating frame, minus this angular velocity of the frame into del del theta prime. Or you have the equivalent relation where I have del del t prime on the left hand side and the original quantities on the right hand side. So 33a and 33b, they are equivalent. Now, this is important as far as this course is concerned. If the flow is steady in the stationary frames, then del del t will be 0. And if it's unsteady in the stationary frame, then del del t will be non-zero. Similarly, if del del t prime is 0, we say the flow is steady in the rotating frame. And if del del t prime is non-zero, the flow is unsteady in the rotating frame. In case of pumps and Francis turbine and Kaplan turbine, the flow will be steady in the rotating frame. Okay. Now, if you look at the difference between these two derivatives, the time rate of change in the rotating frame and the time rate of change in the stationary frame, you see it is omega del del theta of the flow quantity. Now, here omega is non-zero. So, if del del theta is non-zero, then this difference is non-zero. That means both del del t and del del t. So, the flow then is steady in one of the two frames, not in both. However, if you have, say, a pump with infinite number of vanes, then you can argue that del del theta is 0. In that case, the flow might be steady in both the frames. But you will never have a pump or a turbine with infinite number of vanes, so there will be some variation in the angular direction. So the important thing which is not emphasized in the available books is that del del t prime is 0, but del del t is non-zero. Now, if you look at the relation between the vectors, velocity vectors, the radial velocity components are the same, axial velocity components are the same, but since the frame is rotating, the v theta prime is not the same as v theta. You have to subtract omega r from v theta. So this is your w theta. And if you wish to express these three scalar equations in vector form, you can say w is v minus omega cross r. Okay. So these things we have looked at last time, and I also showed you that the material derivatives are the same in the two frames. The important thing is that in the stationary frame, d dt is del del t plus v dot grad, and in the rotating frame, d dt prime is del del t prime plus v prime dot grad prime, or del del t prime plus w dot grad prime. But using the chain rule, we can show that these two 38d and 38f are the same. Now, this I went through this material last time, that the material derivative of Vr is the same as the material derivative in the rotating frame of Wr. But if you look at the v theta component, you have an additional term here. So if you look at the components of the acceleration vector, this I derived last time. Ar is d dt of Vr minus this centripetal term, v theta square by r. So instead of v theta, if I substitute w theta plus omega r and expand this, there will be three terms. First one is w theta square by r. Next is minus 2 omega w theta, and you also have minus omega square r. So you recognize the third term on the right hand side of equation 42 as the Coriolis acceleration, and the last term as the centripetal acceleration. Similarly, if you look at a theta, okay, you will have this additional term 2 omega wr, which again you will recognize as the Coriolis acceleration. So it's useful to look at the acceleration vector, which is in cylindrical coordinates ar er plus a theta e theta plus az ez. Okay, so we substitute the expressions using the relative velocities, and you have these three terms which are similar to what we have seen before in the stationary frame, and you have additional terms. These are the Coriolis terms, and this is the centripetal term. And it's easy to show that these two can be expressed in this form: twice omega vector cross the relative velocity. The other things to note is that if I look at grad of omega square r square by 2, it will be omega square r er. Because if we take the partial derivative with respect to r, del del r of r square by 2 is simply r. And since it's a function of r alone, the del del theta and del del z terms are 0. And these terms which I have cropped up in the equation here, 46, this can be recognized as the material derivative of t prime in the rotating frame. So one can write the acceleration term as d of the relative velocity dt prime plus the Coriolis term and the centripetal term, which I can write as grad of omega square r square by 2. Okay, so this derivation is not very important as far as this course is concerned. For the sake of completeness, I've outlined the derivation. If you're interested, you can go through it. But now we'll see how to use this and come up with relations that are useful for this course. So now we look at Euler's equations of motion for an ideal fluid in a rotating coordinate system. Okay. Now, if we recall, we wrote it in vector form as rho dv dt equal to minus grad of, if I combine the body force term with the pressure, as P minus rho g dot r. So this quantity P minus rho g dot r, we were denoting by the symbol P star. Now in the rotating frame, I will reduce the relative velocity here. So you have the Coriolis term and the centripetal term. And this is d dt prime of the relative velocity. Now this grad term can be moved to the right hand side. And since grad is a linear operator, we can combine this term with this and write this equation simply as rho times this relative acceleration term here, d dt prime of w, plus rho times this Coriolis term equal to minus grad of another modified pressure, which I am denoting by P with two superscript stars. So that is P star minus half of this, or P minus rho g dot r minus half rho omega square r square. So this has the effect of gravity as well as the centrifugal force arising from rotation of the coordinate system in it. Okay. Now one can derive a mechanical energy balance from this equation, which will be useful for this course. Okay. Now that will give you a form of Bernoulli's equation along a streamline, but this will be a streamline in the rotating coordinate system. So first of all, let us look at the equation of a relative streamline in the rotating coordinate system. So I can write it in this form. The position vector r prime is a function of s prime, where s prime is an arc length along the streamline. But r prime is r e prime plus z e prime. Okay. So the theta dependence is coming through this unit vectors. Okay. But the position vector itself has just r prime and z prime. So this equation, the parametric equation, where the parameter in the equation is s prime, I can write as two equivalent scalar equations that the radial coordinate r prime is some function of s prime, and the axial coordinate z prime is another function of z prime. Now if I say es prime is a unit vector tangent to the streamline, the streamline is a line which is parallel, where it's a curve such that at each point the tangent is in the direction of the relative velocity. Relative velocity is w. To make it a unit vector, I divide it by the magnitude, which I am calling capital W. So don't confuse this w with work. Okay. So this is square root of Vr square plus V theta square plus Vz square, and W, the vector, is, I can call it V with the superscript REL for relative velocity, or V prime, which is the absolute velocity V minus omega cross R. So if you look at the vector dr or dr prime, it will be parallel to W. So that is true if dr prime by Vr prime is R prime d theta prime by V theta prime equal to dz prime by Vz prime. And each of these three equations I can also write as ds prime by V prime. So notice that since theta is in radians, it is dimensionless. So we have the scale factor R here. Okay. So instead of using this notation V primes, I'm using W, a subscript-free notation. So this here ds prime is the magnitude of dr prime, this vector, displacement vector dr prime. So it will be d of r prime whole square plus this arc length r prime d theta whole square plus dz prime whole square. Now we start with this equation, momentum equation, in the rotating coordinate system. And of course I have assumed the density to be constant in defining my P star star. So this P star star has a density built into it. Okay. We take the scalar product of each side with the relative velocity W. Okay. Then right hand side, left hand side will have two terms, W dot ddt prime of W multiplied by rho plus this Coriolis term, and right hand side will be minus W dot grad of P star star. But as we have seen, W dot the material derivative is the material derivative of W square by 2 or W dot W by 2. And if I look at the middle term, perpendicular to the plane containing omega and W. So it is perpendicular to W. So if I take again the scalar product with W, the scalar product is 0. So as far as this mechanical energy balance is concerned, this Coriolis term is not going to contribute. Okay. Similarly, this last term here, W dot grad, I can write as ddt prime minus del del. I can add and subtract del del t prime and write it this way. Okay. So these are similar to what we have done before. So I'm going a bit fast. Take this and substitute over here, and you'll see that you have a relation like this. Rho ddt prime W of W dot W by 2 is equal to these two terms. Now I can move the rho inside again this derivative because rho is a constant. I can move this last term on the right hand side to the left hand side. And ddt is a linear operator. So you have an equation of this form, ddt prime of P star star plus half rho W dot W is equal to this unsteady term, del del t prime of P star star. Now P star star is the sum of three terms which I have written here in full. Okay, the static pressure P minus this gravity part minus this centripetal part, and then you have the relative kinetic energy term here. So let us introduce, as we have done before, a symbol V, capital V, V for Bernoulli, and I put a superscript ROT because this is in a rotating frame. So let this quantity in parenthesis P double star plus half W dot W, let us denote it by the symbol V rod. So then this will be the sum of 1, 2, 3, 4 terms. The last one is the relative kinetic energy per unit mass. First term is the static pressure. Second term is the potential energy per unit mass associated with the gravity. And the third term we can say is another potential energy associated with the rotation of the frame. Now of course here we have assumed that omega is a constant. So this equation which you have got, I can write in using these symbols as one term here on the left hand side equal to another term here on the right hand side. D dt prime of B rod equal to del del T prime of B star star. Okay. Now I can expand this, that d dt prime, write it as the temporal derivative del del T prime plus the relative velocity W dot grad prime. Okay. And W vector I can write as its magnitude multiplied by the unit vector, which gives the direction of W. Is del del S prime. It is a directional derivative in the direction of the S prime, which is arc length along the streamline. So the mechanical energy balance reduces to equation number 68. That del del T prime of B rod plus W del del S prime of B rod equal to del del T prime of another variable, which is your P star star. Okay. Now we look at what you may call Bernoulli's equation in a steadily rotating frame of reference. So when the flow is steady in the rotating frame, then del del T prime of B rod as star star will be 0. So the first term on the left hand side of equation 68 and the right hand side of 68, both will be 0. This is an important point to note, because when this will occur when the flow is steady, not in the stationary frame, but in the rotating frame. So in that case, this equation will have only this middle term equal to 0. W del del S prime of B rod equal to 0. Now W is not 0, right hand side is 0. So you can drop the W and write it as del del S prime of B rod equal to 0. So this is true for an inviscid flow of a constant density fluid in a constant gravitational force field, provided the flow is steady in the rotating frame. So if I look at equation 70, I can integrate it with respect to S prime, and you will get B of rod equal to constant along a relative streamline. So the balance of mechanical energy gives you this relation, which you may call Bernoulli's equation in rotating coordinates, that B rod is a constant along a relative streamline relative to the coordinates, rotating coordinate system. And what is B rod? We have already defined it. It has 4 terms: the static pressure, the gravitational potential energy per unit mass, the relative kinetic energy per unit mass, and this additional term which you have not seen before. Okay, so in the translating frame, this third term on the right hand side was not there, but you had something here. Of course, W definition was different. It was the velocity relative to the translating frame. Now it is a velocity relative to the rotating frame. But note this additional term which is coming because this is a non-inertial frame. Okay. So if you have 2 points on a relative streamline, which I denote as 1 and 2, then I can simply write Bernoulli's equation as B rod 2 equal to B rod 1. Or I am writing it now, this big whole thing here, the sum of pressure, potential, gravitational potential energy per unit mass, the centrifugal potential energy per unit mass, the relative kinetic energy per unit mass, which I am writing as W square at point 2 equal to similar terms at point 1. So the subscripts 2 here refer to quantities at point 2. So you have omega 2 whole square times R2 whole square. And here you will have omega 1 whole square times R1 whole square. And there's a minus sign here. Okay. So this is a new term which you have not seen before. So this relation, either you call it 72 or 73, this will hold when the flow, this is the most important thing, which you are not coordinate system. And of course, we are using an inviscid model. So we are assuming the flow is inviscid. The fluid may be a viscous fluid, but it is behaving like an inviscid fluid because strain rates are small. And it's a liquid, so we'll say the density is constant. For us, G is constant. And of course, we have taken a case where the angular velocity, omega, is also a constant. So we are not looking at the transient case when the frame might be accelerating. There might be angular acceleration. Okay. But even when the transient dies out, the frame will definitely rotate at a constant angular velocity. Okay. So any queries regarding this? So the most important thing that we have looked at in the rotating coordinate system is this equation. Borderless equation in the steadily rotating frame of reference. So if there are no queries, then I'll stop sharing this and open another document. Sorry, I got knocked out accidentally. All right. Now we look at another important topic, which is on the centrifugal pump. So this, yeah. Any queries? Okay. So this is a section through what you may call the impeller of the pump. So we have an axis, and mounted on the axis is your rotor, which you call the impeller or runner. Okay. So this is a cut section. So this solid line here is what you may call a front shroud, and this solid line section here is the back shroud. Okay. And this is the passage through which the fluid can flow. Okay. And this is the other view. This is the hub. Okay. This plus here is the center of the shaft. And here I've shown a clockwise rotation. And here you have this, what are called blades or vanes. Okay. So centrifugal pump has a casing, which I have not yet shown, and a rotating part, which you may call the runner or impeller. So this impeller carries a number of curved vanes or blades, and it rotates inside what you may call a casing or housing. So the impeller itself is a rotating solid disc with curved vanes or blades standing out from the face of the disc. So when the impeller rotates, what will happen is liquid will drawn in to the passages. So this gap here is a blade passage. So this side is called the eye of the impeller. Okay. Now let me go down and show you another view. Okay. So here I have shown the casing, which is called a volute because of its shape, or scroll. Okay. And this is the impeller. Okay. It is a disc, and on the disc you have these vanes. Okay. This is the impeller region, and this central part here is called the eye of the impeller. Okay. So in this view, the fluid will enter in the direction perpendicular to the plane of the screen through this central part. Okay, so if you go back to this other view, the fluid will enter through this gap axially. Then it will move into this curved passage, so it will be forced to turn. So if you look at a streamline, it will be parallel to the axis of the shaft at this point and perpendicular to the axis of the shaft as it goes out. Okay. So here there is a Vz component, Vr and V theta are 0. But as it enters here, it will acquire a Vr component because it will turn. This is the radial direction. So between the inlet here, which is the eye of the impeller, it's an annular section, and this dotted line here, which is at r equal to r1. So r1 is this inner radius here, and r2 is the outer radius. So r1 is the inner radius of the vanes or blades, and r2 is the outer radius of the vanes or blades. Okay. So from r equal to r1 to r equal to r2, okay, you can say that the fluid will go out radially. Okay. And when this vane rotates, it will push the fluid, so it will acquire a swirl velocity component or tangential velocity component V theta. But in this region here, between this eye of the impeller and this dotted line here, the fluid will not have any tangential component. Why? Because we are modeling it as an inviscid fluid. Suppose you have a viscous fluid in a circular pipe, and the pipe rotates about its own axis. Okay. Then the V theta that for a fluid particle sitting on the surface of the pipe will be non-zero. The no-slip condition states that V theta then will be the radius of the pipe times the angular speed. And by viscous action, each layer of fluid will start dragging the next layer, and the entire fluid might be set into swirling motion. But suppose I say I'm modeling it as the fluid as an inviscid fluid. In that case, the pipe will rotate, and the fluid, the solid will slip along the fluid. Okay. By the tangential motion of a solid surface, you cannot set an inviscid fluid in motion. An inviscid fluid in motion can be set into motion by a surface which has a velocity component normal to the surface. So it must push the surface. Okay. So we'll assume here that the fluid enters axially without swirl. So in this region, the eye of the impeller, there's no swirl. Swirl it will acquire only when the fluid, after entering, so in the figure on the right, the fluid will enter in the direction perpendicular to the screen. Okay. Then it will turn and it will go out through this gap. Okay. So in this gap here, which you may call the impeller region, okay, there will be a VR and there will be a V theta. There's no VZ over here. Whereas in this region, in the eye of the impeller, there will be no V theta, but there will be a VR and a VZ. Okay. So at this point at the inlet, there's no VR. It enters axially. There's no V theta. But it will turn. So when it's turning, it will acquire a VR. And at this point, the VR will be non-zero and VZ will be 0, and then it will go out radially. Okay. So as the impeller rotates, liquid will be drawn into the blade passages axially at the impeller eye or inlet, which is at the center of the casing of the pump. Then the liquid is caught up by the impeller blades. It is whirled tangentially and forced radially outwards into the diffuser part of the casing, which I showed you over here. So in this figure, the fluid will enter axially through this central circle here, which is the eye of the impeller. It will turn and will go out through the passages between the vanes. So there will be a VR as a V theta component. Then it will be collected in this casing, which has the shape of a volute. So we call it a volute or a scroll. And it will be sent out. There may be another diffuser here. So this side is the outlet of the pump. Okay. And the inlet of the pump is this circle over here in this figure. So the liquid will lead through the circumferential parts of the impeller. And as it moves radially outwards, the fluid will be, or the liquid will be accelerated. So the liquid will gain both velocity as well as pressure when it passes through the impeller. So some work will be done on the liquid by this solid vanes, and the pressure at the outer radius of the impeller will be much higher than the pressure at the inlet radius, and that is the purpose of the pump. So this has the shape of a donut. So this is what you may call a diffuser. So some people call it a scroll section or volute casing. So what this does is it decelerates the flow, thereby reducing its kinetic energy. And when the kinetic energy reduces, the pressure will increase. So there is an energy conversion going on in this scroll casing. So the job of the volute is to collect the liquid and convey it to the pump outlet. Okay. Now the diffuser may be vaneless. So in this figure, in the diffuser section there are no vanes. But you could also have pumps which have fixed vanes which guide the flow to the exit. And the impeller, as I've shown in the first figure, is mounted on a shaft, and it is usually driven by an electric motor. So if I go back to the first figure, this is a shaft. So on the same shaft you will have an electric motor. So when you switch on the power, the motor will rotate the shaft, and this is the impeller which is mounted on the shaft that will start to rotate. Okay. So the vanes will push the liquid here, and it will cause a pressure difference, and liquid will be sucked in axially through this inlet and sent out through the outlet. Okay. So width of this passage at R equal to R1, I'm calling small v with the subscript 1. And this width at the outlet need not be the same here. I'm calling it V with the subscript 2. So this is a sort of annular area. Okay. So the flow area here will be 2 pi R2 V2. And the flow area here will be 2 pi R1 V1. Okay. This is R equal to R1 and this is R equal to R2. Now, the blades may be open or closed. Closed blades are shrouded from the casing by an impeller wall. But the blade may also be open, so it will be just placed inside the casing. And there will be a narrow gap or clearance between the casing and the blade. And we'll show you that for two very good reasons, the impeller blades are what are called backward curved. So if I go back to this figure shows the impeller rotating clockwise, and the blades are bent in the backward direction, backward relative to the direction of the rotation. And if I look at the first figure here also is the same. Okay. So we'll show that there are also radial blades and forward curved blades. Okay, but backward curves are usually preferred. Now we'll look at what is called the pump, which I already talked about, is called a volute type centrifugal pump. So these are provided with a spiral casing or volute casing, or you may call it a scroll diffuser or scroll collector. Okay. So this is a donut shaped diffuser with a circular passage of gradually increasing cross-sectional area. So this will receive and guide the liquid that is discharged from the impeller to the outlet port of the pump. And it will increase the static head of the pressure by reducing the kinetic energy. So look at this. Okay, these are two engineering diagrams. Okay, so left hand side, this small circle here is called the eye of the impeller. So the fluid, when the pump runs, will enter the pump through this eye. and the liquid will enter in the direction perpendicular to the plane of your screen. Okay. So this is your impeller. So the blades of the impeller are between this small black circle and this outer black circle. Okay. And these blades are shown in blue. Now here I've shown a case where this impeller rotates in the anti-clockwise direction. Okay. So the blades are bent backwards. So fluid will enter axially, it will turn, go through these impeller passages, and then move out as shown by this red arrows into this scroll casing, okay, which you may call volute. So the volute will collect the liquid and it will go out through here. So this is the outlet port here. And this is the other view. So I've shown the shaft here, which will rotate with the constant angular velocity omega when you switch on the motor. Okay. And this is the impeller. So this is a section through the front shroud. Okay. And this is the back shroud. So this is the inlet section is the eye of the impeller. So if you look at the side view, the fluid will enter axially, that is in the direction parallel to the axis of the shaft. Then it will turn, so it will acquire a radial velocity. And when it moves out of this impeller over here, okay, it will have a radial velocity as well as a tangential velocity. Okay, so it will be collected here and sent out to this. Okay. Now, if the blade is an open blade, there will be no front shroud, there will be no back shroud. Okay. But the efficiency increases slightly if you have a cover or shroud over the blades. Okay. So the volute is a circular passage of increasing cross-sectional area. So as you go in the direction of this tangential direction, that is the direction of the flow in the volute, the area increases, so velocity will decrease, so kinetic energy decreases and pressure will increase. So it serves to reduce the velocity of the liquid and convert some of the velocity head to pressure head or static head. So the volute casing will collect the liquid, decelerate it, and finally discharge the liquid through the delivery flange, through the delivery pipe or discharge pipe or outlet pipes. So see that these are equivalent terms. Outlet pipe, discharge pipe, delivery pipe, they all mean the same thing. And if you look at the available kinetic energy at the outlet of the impeller, okay, about 25 to 30% of this might be recovered in the form of pressure in a simple volume. So by reducing the kinetic energy, okay, you can reduce about 70 to 75, make the kinetic energy about 70 to 75% of what value it had at the impeller outlet. Okay, and at the exit of the pump, the remainder energy will be in the form of pressure. Now we look at what is called a diffuser type centrifugal pump. So first I'll show you the figure. So here the additional thing is, so this small black circle is the eye. This next black circle here is the edge R equal to R2 of the impeller. And now there will be a short vaneless space followed by some stationary guide vanes, which are shown here in red. So as you can see, if you look at the passage between this red vane and this red vane, it's a diverging passage. Okay. So the liquid after it comes out of the impeller will first move through this diverging passage and then into the volute. Okay. So when it is moving through this diverging passage again, the velocity will reduce compared to what it was at the exit of the impeller. And when the fluid velocity reduces, its kinetic energy reduces, and hence the pressure will increase. So the outlet pressure for this kind of a pump which has a stationary diffuser will be more than in the case of a volute pump. Okay. So in a diffuser type pump, you have a ring of fixed diffuser vanes, or you can call them stationary guide vanes, which surrounds the impeller at its outlet. So after leaving the impeller, the liquid will move in a sort of logarithmic spiral across a short veinless space, and then it will enter the diffuser veins. The divergence angle of the diffuser passage will be somewhere between 8 degrees and 10 degrees. If it's more than that, a phenomenon which you may have studied in your fluid mechanics course called boundary layer separation will occur, and this will reduce the efficiency of the pump. So you cannot make the divergence angle too large. It should be smaller than 8 to 10 degrees. So the diffuser vanes yield improved efficiency compared to the other type of pump which we call the volute pump. This is over, of course, a certain range of operating conditions. Now this diffuser pump, diffuser type pump or simply diffuser pump, is sometimes called by engineers as a turbine pump because it looks like a turbine in reverse. In a turbine, the fluid will flow radially inwards, and here it is flowing radially outwards. So you can call it a turbine in reverse. But this is what I would call an unfortunate terminology. Okay. Because a turbine is different from a pump. In the case of a pump, you are doing work on the fluid and increasing its energy. In the case of the turbine, you are extracting energy from the fluid. But because this is like a turbine in reverse, okay, it is sometimes called a turbine pump. Okay. So later on we'll look at a Francis turbine, and the figure will be similar, only the direction of flow will be reversed. The fluid will enter, in the case of the Francis turbine, through this and will move through this volute into the stationary vanes and into this impeller. Now what I showed you is what you may call a single suction pump, where the liquid enters from one side of the impeller. You could also have a double suction pump where there are two impellers placed mounted on the shaft in such a way that they are mirror images. So liquid will enter from both sides of the impeller. So the impeller looks like two single suction impellers placed symmetrically but back to back, so that one is a mirror image of the other. And advantage of this double suction pump is because of the symmetry, the axial thrust on each side will balance out. So there will be no axial thrust on the bearings. Now sometimes you may have multi-stage pumps where there are two or more impellers arranged on one shaft and they are connected in series. So the fluid coming out of one impeller will be fed into the next impeller and so on. So the total head produced is the sum of the heads generated in each stage. So if you look at just the difference between the outlet pressure and the inlet pressure, it will be much higher than the pressure rise across each stage of the pump. Now let us look at typical centrifugal pump installations. Usually what you may have is an underground reservoir, okay, or a reservoir on the ground, which is usually called a sump, and the pump will be above the level of supply liquid. So this figure I have shown you in the first class. So let us say if you look at the view on the left, you have liquid here in the sump, and this is the suction pipe or inlet pipe. Okay, and this is the shaft. You have the electric motor here. This is the impeller. Okay, and as you can see here, at the bottom here you will have a strainer followed by what you may call a foot valve or a check valve. And this side is the delivery side, the delivery pipe or outlet pipe or discharge pipe, and the water here is simply shown going out. There may be another tank over here. Okay, and if in an experiment, if you want to measure the flow rate, you can have an orifice meter here, an E2 manometer here, and if you want to measure pressures, you can put a Borden gauge here at the inlet of the pump and another Borden gauge at the outlet of the pump. And you may have a full flow controlling valve or regulating valve, which I have shown here symbolically. This is the throttle valve. Okay. Now we'll see that this flow control valve is usually put on the discharge side. If you put it on the suction side, it may lead to what you may call cavitation. We have talked about cavitation before. So this is your volute casing. Okay. Now this check valve is what you may call a non-return valve. It's a one-way valve. Okay. You can call it a foot valve or a check valve. It is installed in the inlet pipe or suction pipe, and it ensures that the flow is one directional. So when the pump runs, the liquid will move vertically upwards. But if you stop the pump, the liquid will not go out. The valve will close. So liquid will not drain out of the pump when it is stopped, or suppose there is a power failure and the pump automatically stops. Now the strainer is a kind of filter screen which is put because there might be some debris, some mud maybe, or pebbles, or maybe some leaves in the sump. So if it is allowed to enter the pump, it will clog the pump. Okay. Now, when a pump is left for several weeks unused, okay, the water will evaporate. So inside the pump, you will have liquid as well as air. And then if you switch on the motor, you will find that it will not deliver water, because water will be churned inside the pump will be a two-phase mixture, and the pressure will not develop as it would when it's fully immersed in liquid. So you have a process which is called priming. The pump must first be primed, which means it's a process in which the pump casing and the supply line are filled with the liquid to be used. So you have to remove all the air inside and make sure that in the suction pipe, the pump and the discharge pipe, there is no air, but only it should be completely full of liquid. And once it is primed, if you keep on using it every day, okay, the liquid will not go out and it will not be filled with air again. And that is ensured by this check valve or foot valve, which ensures that the liquid will stay in the pump. Had the check valve not been there, when you stop the pump, what would happen is the liquid will go out, tend to fall, and there may be a mixture of air as well as liquid inside here. So priming is an operation which removes the air, and you have to do it before you start the pump. Now we need to predict the performance of the pump. So we'll use global balance of now angular momentum. So I'll show you this control volume in dotted lines. We are just considering the impeller part. So this dotted black surface is the inlet to the control volume. This is at radius r equal to r1. And at radius r equal to r2, I've shown another dotted circle, which is the outlet of the control volume. And inside you have veins of infinitesimally small thickness, and you have liquid in the passage. Okay. And when the pump is running, let us say this blades are rotating in the anti-clockwise direction with angular velocity omega. And this is a side view. Okay. So V1, as I said, is the width of the impeller at r equal to r1, and V2 is the width of the impeller at r equal to r2. So the control volume is this annular part here, this annular control volume. So on this figure, you have this surface of the control volume, this surface, this surface. So these are in the region outside the pump. So outside this left surface, the right surface, and the top surface here, you have air. And inside here, this dotted line here is cutting through the liquid region. Okay. So this part is a section. This part is the mirror image of that in this view. And this line is the center line of the axis of the shaft, as well as the rotor. Okay. So we'll consider the system to be the material region or fluid inside which occupies the control volume at time t. And then we'll have balance of momentum in the z direction. So we look at ddt of what we'll call hz. H is the angular momentum and z is the z component. This will be the sum of the moments in the z direction. And this will be ddt of this integral rho r v theta. So the swirl velocity component will come in. Okay. Now the fluid will enter axially here this way and will turn. So at r equal to r1, your v theta 1 will be 0. But at r equal to r2, there will be a v theta. So if you apply Reynolds transport theorem, you will have this temporal term and this flux term equal to the sum of the moments. Now, this is the temporal derivative in the stationary frame. So del del t will not be 0. Okay. So we need to evaluate this unsteady term. Okay. So it is almost 12. So I'll stop here now and continue later. Are there any queries now? So this is a integral over the material region, and this has been converted to integral over the control volume and the flux to the control volume. Okay. So the quantity which I was earlier calling phi, now I put phi is equal to r v theta, because angular momentum is m r v theta. Okay. So I stop sharing this.